Hi everyone, welcome to video lectures on system simulation and modeling model 4 input modeling continued. Now we are going to discuss chi-square test with equal probability. So if a continuous distribution assumption is being tested plus intervals that are equal in probability rather than equal in width of interval should be used. So this has been recommended by a number of authors. So it should be noted that the procedure is not applicable to data collected in class interval where the raw data have been discarded or lost. So unfortunately, there is no easy method for figuring out the probability associated with each interval that would maximize the number, that would maximize the power test of a given size. Here, the power of test is defined as probability of rejecting the false hypothesis H1. However, if using equal probability, so then Pi is always 1 by k is recommended. So then the expected frequency Ei is equal to n into Pi should be greater than or equal to 5. So substituting for Pi which yields n by k greater than equal to 5 for solving k which yield k is less than or equal to n by 5. That we need to be calculating. So if the assumed that distribution is normal, exponential or variable or which are described in the method straightforward, so which indicates that accomplished that exponential distribution if the assumption distribution is gamma or any other distributions, the computations of the endpoint of class intervals is too complex. It could require numerical integration of the density function. So statistical analysis software is very helpful in such cases. So now chi-square test for exponential distribution. So here exponential in the case we need to be taken example of the electronic device component a failure of a device. So any failure component failure device can be because that will be the continuous and exponential distribution suitable example. So the failure of data, so we had analyzed the previous histogram of the data, so which are appear to be exponentially distributed example. So for example, lambda cap. So here exponential, the suggested estimator we need to be taken lambda cap is 1 upon x bar. So that value was the 0.084. That was just assumption. It was computed that the following hypotheses are formed. So here h naught, the random variable is exponentially distributed. Similarly, the random variable is not exponentially distributed. So h naught and h1 can be taken. So in case of exponential, in order to perform the chi-square test with interval of equal probability, the endpoint of the class interval must be found. So which indicates the number of intervals should be less than or equal to n by 5, small n by. So assume that in that example, a small n is 50. So k is equal to less than or equal to 10. So that is we know that how to take the k value. K is less than or equal to 50 by 5. That is it is indicates that 10. So that endpoint can be taken. So it is recommended that 5 to 10 class of interval be used. Let us assume that k is equal to 8. So always prefer k is equal to 6, 8 So it should be less than 10. It depends on the number of the variables or number of data used. Then each interval will have the probability, assume that 0.15 because it is the equal probability. So that we know that how we can calculate the probability. So the pi is equal to probability is 1 by k. So k is that 8. So that is equal to 1.1525. This is a simple example. So finally, we should calculate that we are computed from the CDF for the exponential distribution is capital F of AI is equal to 1 minus E2 for lambda into AI. So AI represents the here end point of ith interval where I equal to 1, 2, k. So f of ai is the cumulative from of we know the 0 to ai. So f of ai is equal to I into p. Similarly, we will get all the values will be taken into the particular part. ai, I start with 1 to 0, 1 to k. So finally, start with 0 to and infinity. So we say end point square bracket is open and parentheses are the closes. So like that we need to calculate, and finally we should compare the critical value from the uh, table need to be calculated, then whether it is a random variable is exponentially distributed or it is not exponentially distributed. Okay, next we will discuss case test, Kolmogorov-Smirnov goodness of fit test. So this test can be used for, especially in case of 100 or large number. Suppose that 50 intervals times in a minute which are collected over a 100-minute interval, which are arranged on the order of the occurrences. So that could be taken in terms of KS test. So there are two hypotheses here. H naught, the inter-arrival times are exponentially distributed, and H1, the inter-arrival times are not exponentially distributed. But this goodness of fit test, KS test, and we had already in the model 3, there was KS test. So that is for the smallest number, the sample size almost 5 or 10 and less than very less than 50 in case. If it is more than that, that test it was not useful. So here goodness of fit can be taken again largest number of case, Kolmogorov-Smirnov test in case of largest distribution. But here, so the interval 0 to capital T 100 minute. So it can be taken into that distribution of interval times capital T1, T2, T3 and dot dot dot. So is exponential in case the arrival times are uniformly distributed on the interval 0, capital T. The arrival time T1, T1 plus T2, T1 plus T2 plus T3, T1 plus T2 plus T3 plus T4, similarly T1 plus 2 plus 3 plus 4 plus 5 plus 6, like that dot 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 up to 100. So here that many point, so that 0 to T can be taken. So the arrival times which are normalized to 0 to 0, 1 interval, so that KS test can be applied on the interval 0, 1. So this interval point will be, we will need to calculate as the 50 data point. So that is that one T1 by capital T1 by T1, comma T1 plus T2 by total number T is the 100. So 0, T 100. So that like that T1 plus T2 plus T3, whatever we have calculated arrival times, that divided by T. So like that T1 plus T2 plus dot 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 T50, because 50 numbers were taken here, 50 divided by capital T 100. So the resulting data will be it will be looking at different values. Then applying that, all will be taken into the same year. The same thing, whatever I told here, T1 plus T T. Similarly, first number, next T1 plus T2 plus divided by T, so dot 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 like that. So all the data, this we will get the resulted data. The following is the this, if you take this example, so calculate the d plus as usual in the formula is same, d minus, then ks stands for capital D is equal distribution maximum of this comma this, we will get then critical value again table AA. So same thing, alpha is always equal to 0.05. So this should be, we will get D is 0.150. The hypothesis that inter-arrival times are exponentially distributed cannot be rejected. But this calculation takes very lengthy. So, in the exam point of view, usually they are not going to ask in the exam purpose. But in general, the application purpose, we should know that how you are going to calculate goodness of it by using the KS test. So next is one of the important point here. After that, so selecting input models without data. So actually without data here, there are four points we need to be considered. In practice, to develop a simulation model, actually perhaps that demonstration purpose or preliminary study before any process data which are available, so that a modeler must be resourceful by choosing the input model and must carefully check the sensitivity of the result to the chosen models. There are a number of ways to obtain the information about a process even if data are actually not available. The first task is point is on the way is the engineering data. So here, what they can do, so often a product or process has performance rating provided by the manufacturer. There are a lot of things need to be taken in the manufacturer. Mean time to failure of any particular disk drive or component, electric component, number of hours will be taken engineering data. Company rules might specify time or production standard. So these values provide a starting point for input modeling by fixing a central value. In such cases, if there is no actual data, but by looking at this, the performance or rating that one, so we could use the any central value. So that is the engineering data. Another expert option, another way without data. So talk to people who are experienced with the process or similar processes. What we are looking to collect the data. So so what we need to do, we need to talk the seniority of the actually field expert. They will in the mouth only they will tell. So they, because they knows the without data they can tell the actual what is the models or actually what is the actual data is required or what are the way to get the entire process, how it is going to run, everything they will have in their own mouth. So that can be done. So that is the, they can provide optimistic or pessimistic or in most likely times. So they might also be able to say whether the process is actually nearly constant or highly variable, and they might be able to define the source of the variability. So next, one more way, physical or conventional limitations. So most of the real processes which have a physical limit on a performance. So computer data entry cannot be faster than a person can type. Definitely. So this is the physical or limitation. Conventional limitations should have that. But here, because of company policies, there could be a upper limit on how long the process may take. Do not ignore obvious limit or bound so that narrow the range of the input process. So this is also one way to need to consider. The nature of the process. So this could be the quite natural. The description or distribution, what we had discussed, which also can be used to justify a particular choice even when the no data are available. So this is the what we need to do. how the when the data are not available, the uniform triangular beta distribution are often used as the input model. So this is also one of the cases. The uniform can be a poor choice because the upper and lower bounds are rarely just likely the central value of in real process. So in the case of triangular distribution, the place much of its probability near the most likely win and much less the extreme. If the beta distribution which is used, then be sure plot the density function of the selected distribution. So the beta can be a usual shape. We know that one. So these are the way to we can say selecting input model so without data. So the next one more part is that one in the input modeling is multivariate and time series input model. Just we will just discuss about why multivariate. Actually, the random variables were considered to be independent of any other variables within the context of the problem. So when this is not in the case, the critical that input models need to be accounted for independence. So otherwise, highly inaccurate in simulation may result. So one example, for example, supply chain simulation include lead time and annual demand for industrial robot. An increase in demand result in increase in the lead time. The final assembly of robot must be made according to the specification of the purchaser. Therefore, rather than the treat lead time and demand as independent random variable, so here multivariate input model should be developed. In such cases, this is an example. In such cases, not only the independent of random variable not sufficient, there are multivariate input model is might be required because of the increasing demand result in increasing lead time in the stipulated time. So looking at that one, we should distinguish actually multivariate input model of a fixed or finite number of random variables from time series input model of a sequence of related random variables. So actually we will see that input model approach this after reviewing the two measure of dependencies. One is the covariance. There are two measures of the dependencies in the input series. One is the covariance and another one is correlations. So the covariance and correlation. So here we should take directly what is the models. That formula is simply we can use that one input series model covariance of x1 comma x2 divided by simple formula 1 upon n summation j is equal to n x of I j. This is the simple into and uh, and x bar mean, so that we will get where x and x sample means and correlation is a rho cap is covariance cap into x1 x2 into standard deviation or sigma of cap, so where the sample variances. So this is the simple formula is given. What about this covariance and correlate? The next one is uh, correlation, also the same thing. So now time series input model. So after taking covariance and correlations, so the time series input model. So this is the one is AR in the bracket 1 model. So this is the Y name we have given AR. So that is the consider we need to take it. So normally in the time series model. So it is the whatever it is in the time series model. So if capital H1 H2 a sequence of identically distributed but dependent and covariance stationary random variable, then there are a number of time series models which can be used to represent the process. So do we need to describe the two models that have the characteristics of the autocorrelation like the form P of H that would be taken it as the correlation of xt comma xt plus h equal to P to the power h. So it is indicates that an autocorrelation decreases geometrically as the lag increases, so that observation from apart near the nearly independent. So now we should discuss the first one is AR1 auto regressive 1. So that is the number we have taken auto regressive 1 model. Consider here the time series model xt is equal to mu plus pi of ux of t 1 minus mu of epsilon of t. So where t is equal to start with always 2 comma 3, where epsilon 2 and 3 are the independent here. So identically, our normal distributed mean zero variance is minus one. That variance is 5. That lies between minus and plus 1. So if the initial value of x1 is chosen appropriately, so then x1, x2 dot 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 are normally distributed with the mean mu variance. This is the standard deviation square divided by 1 upon pi square, and pH of rho h, or you can call it as a pH, that is equal to pi to the power h, where h start from 1 comma 2 dot dot. So this time series model is called as auto regressive order 1. So order 1 model, or we can call it AR of 1 model in short. So this is the just enough for the only what the definition of this AR or not autoregressive model. So the next one is EAR1 model. So that is the just autoregressive one word extra we have added as exponential. So again consider time series model x of t same with the probability pi and with the probability 1 minus pi or t same thing will be taken all the thing initial x1 also chosen appropriately, then capital x1 x2 are exponentially with the mean, because exponentially we have taken here 1 upon lambda, then and p rho of h, or you can call it as a ph 5 to the power h, where h is equal to 1 to this time series model is called exponential autoregressive order 1 model, or capital EAR or bracket 1 model. So next, yes, this definition is enough for the simple calculation. And next is the NORTA, normal to anything transformation. Suppose we want to simulate a random variable x with a cumulative density function capital F of x. Let capital Z be a standard normal random variable with mean 0 and variance equal to 1, and let phi of small z is be its CDF cumulative density function. Then it can be shown that capital R of phi of capital Z is a u of 0 comma 1 a random variable. So as we learned that is in the already in the previous topic. So if you have a the u of uniformity of 0 comma 1 random variable, we can get x by using the inverse cumulative density function CDF transformation. X is equal to capital F to the to the power minus 1, that is inverse. So x equal to inverse f inverse of r, that equal to f inverse of phi of z. So we refer this as the normal to anything transformation, or NORTA, NORTA for a short purpose we are using. Normal, so whatever we are taking normal distribution to anything transformation, normal to anything, whatever we need, so we can transform uniform or inverse or whatever that we can transform. So actually NOTA approach, which requires to evaluate a standard normal CDF of phi of z and inverse CDF also. There is no closed form expression for phi of z and no closed form of expression of f inverse of r in the many distributions. So another point in NOTA, The correlation between the standard random variable z1 and comma z2 is distorted when it passes through the nota transformation, any kind of transformation. To be more specific, if z1 z2 have a correlation row, in general case of x1 should be a f1 inverse of phi1 z1, similarly x2 f2 inverse of phi2 phi of z2. So we'll have a correlation pi of x not equal to rho. The difference is often always small, but in not always in any cases. So this is about the nota transformation or normal to anything transformation. Types of simulation with respect to output analysis. We need to take the certain examples here. The first example, the Shady Grove Bank opens at 8:30 a.m. time 0 with no customers present and 8 of the 11 tellers. So working initial condition and closes at 4:30 p.m. So here the total time TE equal to 480 minutes from 8:30 a.m. to 4:30 p.m. So here the event E is merely the fact that the bank has been open for 480 minutes. The simulation analyst is interested in the modeling the interaction between customer and tellers over the entire day, including the effect of starting up and closing down at the end of the day. So another example, consider the Shady Grow Bank again same but restricted open period from 11 a.m. time 0 to 1:30 p.m. when it especially busy. The simulation run length total TE equal to 120 minutes because 2 hours. The initial condition at time 0, 11:30 a.m. could be specified in a essentially the two-way one. The real system could be observed at 11:30 on a member of different and distribution of number of customer in a system 11:30 a.m. could be estimated. So then these data could be used to load the simulation model with customer time at 0. The second thing we need to consider here, the model could be simulated from 8:30 a.m. to 11:30 a.m. without collecting the output statistics. The ending conditions at 11:30 a.m. used initial conditions for the 11:30 a.m. and to 1:30 p.m. simulation. So another example, the communication system consists of several component plus several backup component. It is represented schematically A, B, C, D. So the consider the system over a period of time again total time T until the system fails. The stopping event is defined by A fails or D fails or both B and C fails. The initial conditions are the that all component are new time at 0. So notice that in the bank example, the previous example, total time 480. First example which minutes on, then example next is the 120. So unpredictable in advance. In fact, total time is probably the output variable of interest as it's the total time until the system breaks down. So one goal of the simulation might to estimate total E of TE mean time to system failure. So another example, consider the manufacturing process of 11.14, that's the example fourth one. So beginning with the second shift, when the complete production process is underway. So it is desired to estimate a long run production levels of production efficiencies for the relatively long period of 13 shift. Okay, the shift may be considered as steady state simulation to obtain sufficiently precise estimation of production efficiency and other responsibility variables. The analyst would decide to simulate for a length of total time is even longer than 13 shift. That is, total time T is not determined by the nature of the problem. So as it was terminating simulation, rather it's easily set by analysis as one parameter in the design of the simulation experiment. So this is the regarding types of simulation with respect to output analysis. So there are these are the examples. So we need to see that what are the simulation types of the simulation with respect to output analysis. So almost all the depends upon the output analysis. So terminating simulation is always is one that runs the some duration of the time. So we should remember that time is the total time capital T of E. So that is a set of events or that stops the simulation. So there are examples, not only this, there are a lot more examples are given. For exam purpose, any 3 to 4 example is sufficient to write any the same example. So that is enough for the exam purpose. So next we are going to concentrate. The next part is the absolute estimation, the measure of performance of their estimation. So here consider actually the estimation of performance of the parameter theta or phi of a simulated system. So it is always desired to have a point estimate and interval estimate of theta or phi. The length of arrival interval estimate is the measure of the error in input estimate. The simulation of output data which are always are y1, y2, y3 and yn. So similarly, for we refer that estimating theta such that output as a discrete time data. So that we should to be count one thing. So here absolute measure of performance and their estimation, that could be there are two type here. The point estimation. So we should start with point estimation. Very we have taken very important equations and part only here. The point estimator theta. So based on data, I told that y1, y2, y3, and yn, which is defined by theta cap is 1 by n summation I equal to 1 to n yi. Okay, so this where theta cap is the sample mean based on the sample of size. So computer simulation language may be referred this as a discrete time collect actually tally or observational statistic. The point estimator theta cap is said to be unbiased for theta. So if its expected value theta, that's if E capital. So expectation, that is the capital E of theta cap equal to theta. In general, capital E of theta cap not equal to theta. So here E of theta minus theta, which is called as the bias in the point estimate. So next one is the confidence interval estimation. So this is the thing to understand the confidence interval fully. It is important to understand the difference between the measure of error and the measure of risk. So both should be taken. One way to make the difference clear is to contrast a confidence interval with the prediction interval, which is another useful of output analysis tools. Suppose what was to take here, both confidence and prediction intervals are based on the premise that the data being produced by the simulation, which is represented by a well probability model. Suppose that the model is the assume that it is a normal distribution, so that with mean and variance sigma or standard deviation square both unknown. To make an example, so yi can be a cycle, that part is produced in the ith replication of the particular. Therefore, theta is mathematical expectation of a capital yi, and sigma, or which is standard deviation, is represented the day-to-day variations of average cycle. Suppose that here our goal is to estimate theta if we are planning to be a business for a long time. Producing the part day, then theta is an irrelevant parameter because it is the long run, the like that mean daily cycle time. So our average cycle time will be, we should have that one average vary from day to day, we know that, but over a long run average of the average will be close to always theta. The natural estimator of natural estimator theta is the overall sample mean of independent replication y cap or y bar equal to summation I equal 1 to n yi by n. So where y is not a particular theta, it is an estimate based on the given sample, and it has error. The confidence interval level measure the of the error, let s square equal to 1 upon n by 1 summation I equal to 1 to n yi minus y uh, bar whole square. So both should be taken here by the sample variance across the R. Capital R is the replications. The usual confidence interval, which assumes always yi are normally distributed. So we should take that equation is y, so y bar plus or minus t alpha by 2 comma n minus 1 into capital S of square root of n. So here where t alpha by 2 and r minus 1 is the quantile of the t distribution with r minus 1 degree of freedom that cut off alpha by 2 of the area of each tail. So we cannot know the certainly exact how far y dash from particular theta, but confidence interval here attempt to bound that error. Unfortunately, the confidence interval to actually bound the error between always y bar and theta. The more replications we make, the less error there in y bar. So, and our confidence interval reflect that because t alpha by to n minus 1 into the s by n always will tend to get a smaller as anyway always n increases. So converging to 0 as an n goes always to the infinity. So actually now we need to take it the normal theory of prediction interval as same as the equation like this y bar plus or minus t alpha by 2n and s of separate root of 1 plus 1 by n. The length of this interval will not go 0 as n increases. In fact, that the limit it becomes theta plus or minus z alpha by 2 and sigma or standard deviation. So to reflect that fact that no matter how much we simulate, our daily average cycle time still varies. So the finally we say that in case of, in summary, the prediction interval is a measure of always risk, and confidence interval is a measure of error. So we can simulate away error by making more and more replications, but so we can never simulate away risk. So which is an inherent part of the entire system. So we can, however, do better job of evaluating risk by making the more number of replications. So this is the we have just discussed about absolute measure of performance, and their estimation is mainly the point estimation and always confidence interval estimation are the important. And next in that module and next video we should discuss about output analysis for terminating a simulation along with verification, validation, and optimization via simulation. That all will be available in the whatever the next videos.